Welcome back, calculators. This is part B of section 4.3. We're going to look at the second problem in your video guide, which is attached here. And you can read that there. We're looking at the graphing guidelines needing to be used from page 1 to graph this function, a pretty decent looking rational function. I've actually taken the liberty of pasting those in here so I don't have to scroll back and forth. And again, it's not like a checklist per se, but it's definitely something we want to be looking at as we analyze this function. So a few things we can do first. Let's grab our intercepts real quick. So we need to grab our y-intercept. So let's plug in 0. And when I do that, we're going to get 10 times 0 to the third over 0 squared minus 1, which is 0 over negative 1, which is equal to 0. So right out of the chute, we have a function that passes through x0, y0, or, in other words, the origin. So we know that is 1 point ready to go. We could look at derivatives. That would give us critical points and inflection points. We could look at, asymptotes, for sure. So let's see here. We have vertical asymptotes where the denominator is equal to 0. And so we could factor that. Or we could use undue operations, whatever works. So I get x equals plus or minus 1. So that means I have vertical asymptotes at x equals positive 1 and x equals negative 1. So I'm going to actually build a little graph down here. I don't know anything really about y values yet, but that doesn't stop me from getting started. So I'm going to kind of acknowledge that at 1 and negative 1, I have asymptotes. All right, and I also found out that I had a point at the origin. And actually, we know by looking at the function's equation that this is an odd function. Maybe you remember that from Algebra 2 and Pre-Calc, which means we are symmetric about the origin. So it makes sense to have a point running through the origin. All right, and let's do some other pieces here. In terms of asymptotes, horizontally, or actually in this case obliquely, I have an oblique asymptote. Welcome back, pre-calculus. Of y equals 10x. And that can be found most commonly by taking the top or the numerator divided by the denominator, but really just the highest order of powers. And when I do that, I get 10x. So that means I have a really steep oblique asymptote. Y equals 10x. And so we've got some interesting things going in here. And remember, oblique asymptotes aren't really super important around the origin. That is more for kind of our extremes. So I'm going to kind of get rid of those pieces, at least in between the asymptotes, the vertical asymptotes, that is. All right. Now, we're going to do a few things here. We're going to want to involve our first derivative, because this is going to allow us to find some potential local mins and maxes. Moreover, kind of where does our function exist in these regions of the graph. And I'm going to show you how to do that as well. So here we go. We need to take the derivative of the original function. That is a perfect example of the quotient rule. So I'm going to list my numerator and my denominator, and then the derivative of each of those things in order to help me complete the quotient rule. And then I'm going to use the quotient rule down below where I've written first derivative. So f prime of x is equal to the derivative of the numerator times the denominator. So that is 30x squared times x squared minus 1 minus the derivative of the denominator times the numerator, which would be 2x times 10x to the third, all over that denominator squared. And when I do my algebra to sort this all out, I get 30x to the fourth minus 30x squared, and then minus 20x to the fourth, all over x squared minus 1 squared. Awesome. And so what we end up with here is 10x to the fourth minus 30x squared over x squared minus 1 squared. And we can factor out the top. Apologies for the super involved algebra here, but this does give us a pretty good opportunity to identify some critical points, because critical points are usually involved when the first derivative is equal to 0. And because the first derivative is a rational function, we are going to look where the numerator is equal to 0. And here we go. We're going to take a look. So obviously x equals 0 is an option. And then x squared minus 3 equals 0 is an option. So we need to be looking at x equals plus or minus negative 3. And when I put those coordinates in to my original function, I'm going to save you the math here, but you can use a calculator to do this. I get 2 more points on my graph. I get a point here and a point here, and those points are at the square root of 3, comma 15 square root of 3, and negative root 3, comma negative 15 root 3. And because of the guiding of my asymptotes, I actually kind of can start sketching already. And I know I have these cool looking pieces doing this sort of thing. All right, and then the only thing we need to do is figure out the middle part of our function. We know we have a point at the origin, and we know that this piece is going to be symmetric, and we know we have asymptotes. So either our graph is taking this shape, or, and we'll erase that because we don't know yet, or our graph, this center region, is taking this shape. And maybe you know, and maybe you don't, and sometimes there are lots of different ways to figure this out. Here, because we are dealing with a pretty gross rational function, I'm going to go back to our first derivative. And what we can do is we can look at a sine graph of the first derivative to figure out if our graph is increasing or decreasing on this interval. So we're going to involve -1, we're going to involve 0, we're going to involve 1, and we're going to have all of these pieces involved here. So that is going to be 10x squared, and by pieces I mean factors. X squared minus 3 and x squared minus 1 squared. Now we are looking for the sign here, and we know that 0 is going to make our first derivative equal 0. So we know that this sign here is going to be 0. But we are really looking what's happening around 0. So here we go. The way we do this, we look at the sign of 10x squared. 10x squared is going to be a positive function. Its y values are positive everywhere except at x equals 0. All right? And the same thing with the denominator of the function. That is going to be positive everywhere except at the asymptotes. So what we're really concerned with is this x squared minus 3 piece. Where is that positive and where is that negative? Well, around 0, we could just plug in 0. 0 squared minus 3 is negative 3. And we know that that gives us a negative function. That is actually going to be a negative function all the way out until negative root 3 and positive root 3. So if we are looking for what happens in between our function from negative 1 to positive 1, we are going to find that the sign of the graph, a positive times a positive, is a negative. And the same between 0 and positive 1. So because my first derivative is negative in that region, that means my graph of my original function is decreasing, which means that because it's an odd function and because it's decreasing, this is my only option for how this center region can look. And after all that, with a little bit of algebra and a little bit of calculus, I've got a pretty good looking graph with all the intercepts and critical points ready to go. This is a video you might want to watch a couple times. This is a video and particularly a problem you might want to talk to your calculus teacher about. You can always reach out to me via email or in the comments of this video, or you could reach out to your teacher directly. But this is a great example of a pretty difficult function to graph. Within your problem set, you'll have some that are a lot easier. You'll have some that are kind of similar difficulty. But I wanted to make sure that you had one ready to go. If you have any questions, be sure to ask, and we'll see you next time. Thanks. Bye.